You sit quietly and think about yesterday. It feels sealed off from you as though a door has closed forever and whatever happened there has slipped into nothingness. We speak casually about the past being gone as if reality itself deletes its earlier drafts while moving forward. Yet the deeper one looks into physics, the more unstable that everyday assumption becomes, because nowhere in the fundamental equations of motion does nature include a command to erase what has already occurred. Instead, the laws describe transformations of states, fields evolving into fields, particles interacting and redistributing energy and momentum, information flowing from one configuration into another. And if something is transformed rather than destroyed, then perhaps what we call disappearance is only a change in accessibility rather than an ontological annihilation. The sensation that the past vanishes is intimately connected to irreversibility. We watch cream mix into coffee and never spontaneously unmix. We observe a shattered mirror and never see shards leap upward into perfect alignment. And from childhood we internalize this asymmetry as proof that time itself is marching in a single direction. But when physicists write down the microscopic laws governing atoms and photons, they do not insert an arrow pointing forward. Newton's equations remain valid if time is replaced with its negative. Maxwell's equations permit solutions that run backward. And even the quantum mechanical Schrödinger equation evolves in a perfectly reversible way, as long as the system remains isolated, meaning the deepest mathematical description of change does not privilege the direction that human experience finds obvious. Which implies that irreversibility emerges not from basic law, but from statistics. Entropy measures the number of microscopic arrangements compatible with a macroscopic state, and because disordered states correspond to far more microscopic possibilities than ordered ones, systems overwhelmingly evolve toward higher entropy simply because there are more ways to be disordered than ordered. A glass resting intact on a table corresponds to a narrow range of atomic arrangements, while a shattered glass corresponds to an astronomically larger set. So when the glass falls, the movement toward fragmentation is not enforced by a time-directed law, but favored by combinatorics, and this statistical gradient creates the arrow we perceive, yet statistical tendency is not the same as deletion. When the glass shatters, the information describing its earlier shape does not vanish into metaphysical darkness. It becomes embedded in the trajectories of fragments, in vibrations propagating through the floor, in slight air currents created by motion, in photons scattered at each collision, meaning the record of that intact glass continues to exist in redistributed form. Light provides a simple but powerful illustration of this principle, because every object constantly scatters photons carrying detailed structural information outward into space. The light reflecting from your face at this moment does not disappear when it moves beyond your sight. It travels outward potentially forever, decreasing in intensity but not in informational content. And if one imagines an advanced observer located sufficiently far away capturing those ancient photons with unimaginable precision, that observer could in principle reconstruct scenes from what we consider the past, not because time reversed, but because the information was never erased. It simply propagated outward beyond our local ability to retrieve it. Quantum mechanics strengthens this picture with the principle of unitary evolution, which guarantees that the total information encoded in a closed quantum system remains constant over time. Amplitudes change, phases evolve, systems become entangled, but the mathematical structure preserves the completeness of description. When two particles interact, a joint wave function carries correlations reflecting that encounter, and even after separation those correlations persist, meaning their shared past is not stored in a vault but expressed in relational structure. And as interactions multiply, entanglement spreads through the environment in a process known as decoherence, distributing phase relationships so widely that interference between alternatives becomes practically impossible. Yet practical impossibility does not imply fundamental erasure. It implies that reconstruction would require reversing the state of an enormous portion of the universe, something beyond capability, but not beyond theoretical allowance. I'm new this enough in Tyre, a place that I'm right as he made in the fourth. It's out to be bingo solo looking crowd. Foscus was like somehow not that sort of new gravity. Relativity further challenges the notion that the past is annihilated by revealing that simultaneity depends on the observer's state of motion. In a space-time framework, events are coordinates within a four-dimensional geometry rather than points sliding along a universal timeline. Different observers slice this geometry into past, present, and future differently depending on velocity. And the absence of absolute simultaneity undermines the idea of a single flowing present sweeping away older events. Instead, all events simply occupy positions in space-time. And the fact that you are no longer located at earlier coordinates does not imply they have ceased to exist any more than the fact that you have walked north. It implies the south has vanished, which suggests that disappearance may be a feature of perspective rather than reality. Memory itself emerges from thermodynamic processes that increase entropy overall. while carving stable ordered patterns locally within neural tissue. When you remember an earlier day, you are activating a physical structure shaped by past interactions, and that structure persists only so long as biochemical stability allows. When it degrades, access fades, and we interpret fading accessibility as the fading of the past itself. Yet the broader universe still contains photons scattered from that day, chemical alterations initiated by that day, and correlations entangled with countless particles that interacted with your body and environment. So while your personal recall may vanish, the physical imprints remain woven into the evolving state of the cosmos. Even on cosmological scales, the universe demonstrates its refusal to erase. The cosmic background radiation still carries subtle fluctuations from the earliest fractions of a second after the Big Bang. Gravitational waves propagate carrying signatures of mergers that occurred billions of years ago, and the distribution of galaxies reflects primordial quantum variations amplified over cosmic time, all of which show that present structure is saturated with memory of previous conditions. Not metaphorical memory, but measurable encoded information accessible through careful observation and analysis. From this vantage point, what we call the past being gone is better described as the past being thermodynamically inaccessible, its informational fingerprints diluted across astronomical degrees of freedom, unrecoverable in practice yet retained in principle. And this distinction matters because it reframes time not as a destroyer of reality but as a parameter in transformation. The universe does not operate like a typewriter replacing lines as it moves forward. It operates like a system continuously rewriting itself in a way that contains traces of all prior states within its present configuration. And this realization sets the stage for a deeper complication introduced by quantum measurement, where even the definiteness of a single narrative past becomes something that emerges only after interaction with the environment, when the past is not a single story. In the first part, we explored the idea that physics does not truly erase events, but redistributes their information into the evolving structure of the universe. And now we move into deeper territory where quantum mechanics forces us to reconsider not only whether the past disappears, but whether it was ever a single fixed narrative before it became entangled with the world. Because the unsettling implication of quantum theory is not simply that information is preserved, but that before certain interactions take place, the description of what happened may not even be uniquely defined in the classical sense we are accustomed to. Consider the double-slit experiment, which has been called the central mystery of quantum mechanics. A single particle such as an electron is fired toward a barrier containing two narrow openings. And on the far side, a detection screen records impacts if both slits are open. And no measurement determines which slit the electron passed through. The resulting pattern is not one of two clumps, as classical intuition would predict, but an interference pattern indicating that the particle behaved as though it traversed both paths simultaneously. Yet if a measuring device is placed to determine the path, the interference disappears and the pattern shifts to reflect behavior consistent with the particle traveling through only one slit. And what makes this experiment troubling is not merely the dual wave particle nature, but the implication that the description of the electron's earlier journey depends on whether which path information becomes available later in the setup. It would be easy to misinterpret this as the future altering the past. Yet that phrasing smuggles in classical assumptions that quantum theory transcends. Because in the formulation developed by Feynman, each possible path from source to detector contributes an amplitude to the total probability. The particle does not choose a path in the ordinary sense. The mathematics instructs us to sum over all possible histories, and only when interaction with a measuring device entangles those alternatives with the environment does one class of history cease to interfere with another. What we call collapse corresponds to decoherence, spreading phase correlations into countless environmental degrees of freedom so thoroughly that retrieving coherent superposition becomes astronomically improbable, and thus the classical appearance of a definite single path emerges not because alternate possibilities were deleted, but because they were absorbed into environmental correlations beyond practical recovery. Delayed choice experiments intensify this conceptual tension by arranging matter so that the decision to observe or not observe which path information can be made after the particle has already passed the slits, and yet the statistical outcomes conform to the measurement configuration chosen at the last moment. This does not imply backward causation in a simplistic sense, but rather demonstrates that the experimental arrangement as a whole defines the physical description. The quantum system cannot be assigned a classical trajectory independent of the full context of measurement. The past in quantum mechanics is therefore not a story existing with absolute independence from future interactions, but part of a relational web in which outcomes emerge through entanglement across space-time regions. Decoherence provides the key to understanding why everyday objects appear to have well-defined histories, while microscopic systems do not. because macroscopic systems constantly interact with their environments, exchanging photons, phonons, and countless other quanta, rapidly entangling with surrounding matter in such a way that superpositions between macroscopically distinct states lose the ability to interfere almost instantly, and when interference becomes inaccessible, alternatives effectively become separate branches in the description, though the underlying evolution remains unitary and information preserving, meaning the definiteness of the classical past is a consequence of environmental entanglement rather than fundamental erasure. This perspective transforms how we think about recording events. When a camera captures an image, the light interacting with the sensor becomes entangled with electronic states that then influence chemical or digital storage media, cascading into macroscopic stability, and each step disperses information further into the environment, multiplying correlations that make reversal practically impossible. Yet at no stage does the mathematics indicate deletion. Instead, it describes proliferation of relational structure, so that what we call a recorded past is simply a configuration of correlated subsystems, robust against decoherent disruption. And the asymmetry we experience arises because entropy growth makes such correlations stable toward one temporal direction, given the low entropy initial conditions of the cosmos. The black hole information paradox once threatened this tidy picture by raising the specter that information falling into a black hole could disappear irretrievably, apparently violating unitarity. But decades of theoretical exploration have produced strong arguments that even in black hole evaporation, subtle correlations encoded in outgoing radiation preserve the information in scrambled form, reinforcing the principle that the universe does not truly forget, even under extreme gravitational collapse. Instead, it redistributes informational content in ways extraordinarily difficult to decode, yet still present in principle. What emerges from this quantum view is a reframing of the past as a constraint encoded in present correlations, rather than a vanished chapter sealed off from reality. The state of any system now reflects an immense network of prior interactions, woven into its entangled structure, and although classical language tempts us to imagine a singular deterministic sequence stretching backward in time, quantum mechanics advises caution. The past that is accessible and definite is the one that has become decohered and redundantly recorded across many subsystems, while alternative histories that were once mathematically included have lost their capacity to influence observable outcomes due to environmental entanglement rather than annihilation. In this sense, the universe resembles an ever-expanding archive in which each interaction writes itself into the fabric of the whole, not in a centralized ledger, but distributed across correlations linking particles and fields throughout space-time. And our perception of a clear, fixed past arises because those correlations become stable and overwhelmingly unlikely to reverse under entropy growth. Yet beneath that classical stability, the unitary evolution underlying quantum theory continues to carry forward the complete informational richness of what has transpired. And this subtle interplay between determinism, probability entanglement, and thermodynamic asymmetry sets the stage for the final step of our exploration, where relativity and quantum theory together challenge the very notion of temporal flow, suggesting that becoming itself may be an emergent feature of how conscious systems traverse a structure that in its totality does not move at all. If nothing is erased, what is time? Having seen that fundamental laws do not delete information, and that quantum mechanics preserves correlations even as they become unimaginably complex, we arrive at the final and most unsettling question. If the past is not truly destroyed but transformed and encoded into the structure of the present, then what exactly is the passage of time that makes us feel as though moments are constantly slipping away? Because the experience of flow seems undeniable, yet the mathematics describing the universe appears indifferent to that feeling. Relativity first undermines the idea of a universal flowing present by revealing that simultaneity depends on the observer's motion. Two events that appear simultaneous in one frame of reference may occur at different times in another. And this relativity of simultaneity dissolves the possibility of a single cosmic now sweeping uniformly across the universe. Instead, space-time is described as a four-dimensional manifold within which events are coordinates, not ephemeral sparks that ignite and vanish. And once events are treated as locations in this structure, the notion that the past has ceased to exist begins to look like a feature of perspective rather than a feature of ontology. Well, what is often called the black universe interpretation, all events past, present, and future coexist within the space-time manifold, not as evolving entities, but as elements of a geometric whole, and the feeling that time flows resembles the experience of consciousness moving along a world line through that structure, much like a reader progressing through pages of a book that already contains its entire narrative. From the perspective of the reader, earlier chapters feel behind and later chapters ahead. Yet the book itself is complete, and if space-time is analogous to that book, then nothing in it is erased as one moves from page to page. It is simply encountered sequentially by beings embedded within its structure. The resistance to this view arises from our intuition that the future is open and the past fixed. Yet, physics suggests that this asymmetry may be rooted in thermodynamic boundary conditions rather than fundamental dynamics. The universe began in a remarkably low entropy state and has been evolving toward higher entropy configurations ever since. And because entropy increases, statistical tendencies favor the formation of stable records in one temporal direction. Memories accumulate from lower entropy to higher entropy states. Records of yesterday exist today because entropy growth allowed correlations to spread and stabilize, whereas records of tomorrow do not exist today because the relevant interactions have not yet occurred along our world line. So the openness of the future may reflect a limitation in record formation rather than a metaphysical indeterminacy. Quantum mechanics adds nuance by evolving the universal wave function smoothly without reference to a preferred present moment. The Schrödinger equation does not single out now as special. It simply describes continuous transformation of amplitudes. And in interpretations that retain universal unitarity, the branching of outcomes through decoherence gives rise to effectively classical worlds, in which observers experience definite results. Yet these branches arise from the deterministic evolution of a global state, not from the destruction of alternatives. So becoming may be an emergent feature of how subsystems with limited access to global information register entanglement changes along their trajectories. From this vantage point, what we call the passage of time might be understood as the accumulation of correlations within localized systems that process information asymmetrically due to entropy gradients. Consciousness is a physical process embedded in neural matter. Neurons fire in patterns shaped by prior interactions, and those patterns integrate sensory inputs while retaining traces of previous states, creating a narrative sense of continuity. But that narrative continuity does not require that earlier space-time coordinates vanish. It requires only that the brain encodes them in durable structures while continuously updating itself as new interactions occur. This perspective does not trivialize human experience of loss or change, because accessibility matters profoundly for creatures like us. An event that cannot be reconstructed or revisited feels gone, even if its informational imprint remains dispersed throughout the cosmos. When a loved one dies, the neural and relational patterns enabling interaction dissolve, and no practical reversal of the astronomical correlations involved lies within reach. So the emotional reality of finality persists, even if the physical ledger of the universe has not erased the traces of their existence. The photons they scattered continue outward. The gravitational effects of their mass remain embedded in space-time curvature. The chemical changes they triggered propagate forward, meaning what we mourn is not annihilation, but irretrievable transformation. At this stage, the philosophical temptation is strong to impose metaphysical conclusions. Yet the careful discipline exemplified by Feynman advises restraint. Follow the equations faithfully and do not insert comforting stories or dramatic paradoxes beyond what the mathematics warrants. And what the mathematics warrants is striking enough. It tells us that information is conserved in quantum evolution, that space-time accommodates all events without privileging a universal present, that entropy generates asymmetry in record formation, and that apparent irreversibility reflects statistical overwhelming probability. Rather than microscopic prohibition, combine these principles, paint a picture of a universe in which nothing is fundamentally deleted, though everything is constantly transformed. Thus, when we say the past has not really gone away, we do not mean that we can revisit it like a preserved recording, nor that classical causality runs backward altering previous facts. We mean that the physical structure of reality retains within its present configuration the encoded consequences of prior states. That what feels like disappearance is the movement of information into degrees of freedom beyond our retrieval. And that the sensation of flowing time may emerge from the way entropic gradients shape conscious processing rather than from a cosmic engine consuming moments as fuel. In this framework, the universe resembles not a stream carrying events off a cliff into oblivion, but an ever-evolving tapestry, in which each new thread interweaves with those already laid down, altering patterns without tearing out earlier fabric. And we as observers trace paths through this tapestry, accumulating perspective while mistaking limited vantage for ontological deletion. So perhaps the most accurate conclusion, consistent with the spirit of Richard Feynman, is not mystical reassurance, but intellectual humility, the recognition that our everyday language of gone and coming may be inadequate to describe a reality whose fundamental laws speak only of transformation, correlation, and structure, leaving us with a universe that does not forget but continuously rewrites itself in a manner that carries all prior chapters within the evolving present.